Okay, so number one on the review basically gives you this equilibrium right here. And it's asking you, doing which of these four, so this is a multiple choice question, what will increase the solubility? Now, we talked about solubility a little bit, but I wanted to give you guys a little bit more detail about it. But solubility is basically when something dissolves, right? So solid going to aqueous, okay? Wrong compound, but it's this right here. So solubility is the forward reaction right here. So if you want to make a note of that right here, solubility is when a solid dissolves into ions. And so in this situation, it's going to be the forward reaction. So basically what the question is asking, what do you need to do to make the forward reaction happen more? So in other words, how can you make this equilibrium shift which direction? Right, yeah, you want it to go forward, so you want equilibrium to shift right, and these are your options. So let me give you guys about 2-3 minutes. See if you could think about it, talk about the person next to you. Which one of these four things will shift equilibrium to the right? Okay. So I think easiest way, I'll just give you the answer. It's going to be A. It's pretty simple. And it's because if you add LiCl, you are adding reactant, right? And remember the chandelier principle? If you add reactant, it's going to shift it the other way towards the product. And going forward is where you dissolve, so that increases solubility. Okay, let's talk about why B, C, and D don't work though. So let's look at B. If you take a look at B, you are adding Li+. Li+ is a product. So if I add more of this, which way is equilibrium going to shift? Yeah, to the left. So that's the problem. So that's why B doesn't work. Same thing with C, because it's chloride, right? It's also going to shift it to the left. The one that might have thrown you off a little bit is D, where you add NaCl. But let's talk about why this one also doesn't work. So if you put NaCl inside of a aqueous solution, what does NaCl do in water? Dissolves into Na+ and Cl-. And if you notice, by adding NaCl, what you're essentially doing is you're adding more Cl- because it dissolved. You're just adding it in a different form. And so this will also shift it backwards to the left. Okay? So that was a little tricky because it's not in the equilibrium, but because it dissolves, it's going to shift it as well. Okay? So something to keep in note. All right, let's move on to 2. So for 2, it says you got an equal number of F2 and Cl2 in a closed container, and it goes to equilibrium. And then you have the equilibrium constant right here. It's asking us what is the relationship between FCl and F2. Okay, so I'll give you guys a couple minutes to try this out. This is framed a little bit weird, and the answers look a little bit complicated. But see if you guys can use the equilibrium constant to figure out which one of these options is correct. This is a multiple choice as well, so you're picking one of the 5. So take about 2-3 minutes, try it out, and then we'll go over it together. Okay, so we are looking for the relationship between FCl and F2. Okay, so we have the K value right here. So I'm going to start by just looking at the K constant expression. So we know that the products go on top, right? And since it has a coefficient of 2, you got to square it, divided by F2 and Cl2. Okay, so far so good? Yeah. Okay. So this is the equilibrium constant expression. Now, we can actually simplify this a little bit based on the information that we have up here. It says we have an equal number of moles of F2 and Cl2, right? That means these two values are going to be equal to each other. And if you look at the answers, do we have Cl2 in any of the answers? No, right? So that means that we want it in terms of F2. So what we're going to do is we're just going to substitute this as F2 because they're equal to one another. It's going to be the same values. Okay. All right. So far, so good? Okay. Let's simplify it a little bit more. We got 2 F2s. If you multiply them, you get F2 squared. And we know that that is equal to 5 times 10 to the negative 5. Okay. All right. Everybody good? Okay. We could simplify this by finding the square root of both sides. And then that'll get rid of the squares. So on this side, we'll get rid of the squares. And then I'm not going to solve this out because it's not really necessary. If you did solve it out, that's fine as well. And if you look at the formatting, you see how FCl is isolated on the left side by itself for all the answers, right? So what we're going to do is we're going to isolate FCl by multiplying by F2. So if you multiply both sides by F2, you'll get this right here. All right, so you can already knock out a bunch of answers just by getting here, right? Okay, obviously they're not going to be equal. Obviously it's not this one because it's a square root, and you're not dividing it, so you can cancel out E. So you're left between A and C, and you basically... Why are you guys so happy? Oh. Yeah, 50%, yeah. All right, so if you take a look at this, let's think about what this value means. So we know that this is going to be, is it going to be greater or less than 1? This is going to be less than 1. So that means that this is going to be a decimal times F2. That means that FCl is going to be greater. All right, so if we take a look at this, we got an equilibrium, and so we start by writing the constant expression, and this is just the formula. So we're going to write K equals, and then products go on top. So product is CO, carbon monoxide, and then coefficient is 2, so you got to square it. And on the bottom, you put the reactants. However, if you take a look at carbon, it is a solid, so we omit that from the expression. We only add O2. So there you go. That is your equilibrium constant expression. Yeah. What's that? What's gas?
The constant. Like P and like.
Oh yeah. So yeah, you could do that as well. Yeah.
Well, does it matter?
Well, yes and no. So it's not asking specifically for pressure, and if you look at the actual units, the values that are given, it's moles and liters. So you could do pressure. You wouldn't be marked down for that, but molarity is probably the easier one to find. Yeah. So great question. You wouldn't be marked down for that. Yeah, as long as you are consistent with what values you're using to solve for. Yeah. And eventually you're gonna get the same numbers because they'll just kind of factor out that way. All right, so let's go to the value of the equilibrium constant. Now we're going to plug our numbers in. So we're just going to plug our numbers in right here. If you look at CO, we don't have a value for that. So we need to figure out, we've got to use an ice table to figure out the equilibrium concentration. So we're going to have 2C, which is a solid, so we're going to omit that, plus O2 goes into equilibrium, 2CO. And then we're going to set up our ice table. Like we said, carbon is solid, so we don't include that in our ice table. What is the initial value for O2? Yeah, 0.75. If you wanted to divide it by 3, get molarity, you can, but it's going to end up with the same numbers. You can't find pressure because you don't have the temperature, so you wouldn't be able to use the ideal gas law here. So we're just going to keep it easy, and we're going to do 0.75 moles. Oops, where's my 5? All right, what's our initial value for CO? 0. It's not mentioned, so it's 0. And so what is the change for O2 going to be?
0.25.
Yeah, so it is going to be minus x, right? Because you're going to be losing this, and then you'll gain 2x right here. Okay, but it gives you the actual value for O2 at equilibrium, which is going to be 0.1. Okay. However, this one did try to trip you up with the units of measurement. What is the unit of measurement for O2? Yeah, moles over liters. So we either need to turn this into moles, or we need to turn the 0.75 into molarity. Okay, so I'm going to turn the 0.75 into molarity. So it'll be 0.75 divided by 3, and that'll give you 0.25. So this will be 0.25 moles over liters. Okay, so if you missed that, very easy miss right here. 0.1 is given in moles per liter. but you are given just moles, so you need to divide it by 3 to get the 0.25. Yeah. Okay, so little ways that you can get tripped up. Just make sure you're very detail-oriented with the actual units of measurement. Okay, that's going to give us the actual value of x. It'll just be 0.25 minus 0.1, so that means you lost 0.15 molarity. Okay. All right, and then that's going to give you the actual value for CO at equilibrium, and it's going to be 0.3 moles per liter. Okay, so little things that could catch you off guard, but hopefully you at least got the minus x and the plus 2x, and the minus x is the difference. Okay. All right, from there, pretty simple. We just take our expression and we just plug and chug. Top, we got CO, which will be 0.3, so it'll be 0.3, but you got to square it. And on the bottom, you'll have 0.1. Okay, just solve from there. Any questions? That's all right? And then you'll get 0.9 as your equilibrium constant. Okay, so pretty simple ice table problem, but you can see how little things, right, little units of measurement could really trip you up. If you didn't convert to molarity here, and you just solved it out, then you would still get partial credit for setting up the ice table correctly, but you would lose, obviously, some points for getting the wrong values. Do you have a question? Was that your question? Yeah, no worries. Okay. All right, so just keep that in mind when you are doing the exam. Just keep track of the units of measurement. Okay. All right. So if you have questions, you can ask me about 3 still if you're finishing copying it down. But try number 4 with the person next to you. I'll give you about 3 minutes to do this, and then we'll go over together. All right, so we have this container, this system right here, and then it says that, or it gives you the, what is it? Oh my God, I just had a brain fart. It gives you the values of how much of each compound you have. So first question you need to ask is this at equilibrium? No, probably not, right? Because it's asking you how is the reaction going to proceed. So there needs to be either a shift to the left or to the right. So we got to figure out how it's going to shift. And in order to do that, what do we need to calculate for? Q. We got to calculate for Q. Q is calculated the same way we calculate K. We just use the non-equilibrium values, right? So Q is going to be the concentration of NH3 squared divided by the concentration of N2 and H2 cubed. Okay, and so what we're going to do is we're going to take these values right here. We're going to plug them into this the equilibrium constant expression, and then we have to compare it with the K to figure out if it's going to shift to the left or to the right. Okay? So let's plug in our values. If you look at NH3, it'll be 0.54, and we're going to square it, divided by N2, which is 0.28, and then we got 0.16, and that'll be cubed. Okay? All right, if you solve it out for Q, I got about 254, something around there. Okay, if you got the 0.25, that's fine, but it's not going to make a big difference. Because all we're going to do with Q now is we're going to compare it with K. Okay, so we're going to compare these two values. So if we take a look at it, Q is obviously greater than K, right? So we got to figure out, what does that mean? Does that mean we have too much product, or do we have too much reactant? So if we take a look at K is the ratio at equilibrium, right? If Q is bigger, does that mean our numerator is too big or the denominator is too big? It means the numerator is too big. If Q is greater than K, that means the numerator is too big. And we know that products go on the numerator, and so that means that we have too much product. Okay, everybody tracking with the logic? And if we have too much product, which way is equilibrium going to, or which way is the reaction going to shift? To the left, right? So that's going to shift left. So that's the kind of logic that you want to go through, and that's going to get rid of half our options. So C and D are incorrect because it's going to shift to the left. All right, next we just need to figure out, is pressure going to increase or decrease? So we just got to figure out, is there more pressure on the left side or the right side? For this, we look at the moles of gas. How many moles of gas are on the left side? 4 moles of gas. And how many are on the right side? 2. So if it shifts to the left, is pressure going to go up or down? It's going to go up. Yeah, so it's going to be B. Okay, so that's typically what a Q versus K type of problem would look like on the AP test. I think you have one very similar to this on your exam as well. I haven't looked at it in a while, so I don't know. Alrighty, so let's move on to number 5. I think 5 is very similar. This is also a Q versus K type of problem, so we just did one like that. So see if you could try this out. I'll give you about 3 minutes to do 5. And then if you finish early, I guess you can start 6 as well. But see if you can do 5 on your own, and then we'll go over it together. All right, so for 5, we're actually kind of working a little backwards here because it talks about the pressure first, and that's how we can figure out how equilibrium is going to shift. So it tells you that you have a container with these 3 gases, and then when equilibrium is reached, pressure has increased. So we got to look at the equation and figure out which side has more pressure. Which side has more pressure? The right side, right? That means that the system has shifted to the right. Okay. So we just need to figure out, does Q have to be bigger or smaller in order to make the system shift to the right? So we can actually get rid of all the left ones, and then we just need to compare Q versus K. So if the system has shifted to the right, let's think about this logically. Before it shifted, did we have too much product or too much reactant? Yeah, we had too much reactant. Okay, so we had too much reactant. Okay, if you had too much reactant, does that mean the numerator or denominator was bigger? The denominator was too big. So the denominator was too big. And if the bottom of a fraction is too big, does that make it smaller or bigger? Smaller, yeah, because it makes it go down. So it's going to be smaller, the ratio. Okay, so smaller ratio. Okay, which means that Q was less than K. Okay. If you just memorized what the Q versus K relationship means, you can just easily figure that out. Or you can go through all the math stuff. I'm just giving you the reasoning behind it. Okay, but you can just memorize it outright if you want to. I just personally hate memorizing, so I just did it this way. Alrighty, you guys good?
Yeah.
Okay, this unit's pretty easy?
Yeah.
I hope so. Alright, so let's look at 6 now. 6 is something that we talked about, and we actually drew a graph already in our notes. But we have this system, and it's at equilibrium, okay? Now, it tells us that some of the Cl2 is removed, and a new equilibrium gets established. And you need to draw a graph how Cl2 will change over time as it's removed and the new equilibrium is established. So if you guys forgot, the graph that you're going to draw is going to have an x and y axis, obviously. The x-axis is going to be time, and the y-axis is going to be Cl2, the concentration of Cl2. Okay, and let's see if you guys remember. See if you guys can draw the graph of how the concentration of Cl2 will change as equilibrium is disturbed and then it is reestablished. But let's talk about why the graph will look the way it does. So we're going to draw a straight line to talk about how we are at equilibrium, because when you're at equilibrium, the concentration doesn't change. When you remove Cl2, obviously it's going to drop because you lost Cl2, so this is the removal. And then after that, new equilibrium is going to be established, but the key thing you want to notice is that it will never get to the actual equilibrium level. It will always be lower, just because you don't have enough mass now to get back to the original equilibrium. Okay? And then you would taper out with another straight line. So this right here will be new equilibrium. And then this part right here, the curve back up will be, if you want to be super specific, this will be the the chandelier principle. Okay, but it's just the new equilibrium being established. Okay. Everybody good? All right. Let us move on. So, I forgot an N. N. Okay, so let's have you guys try number 7. This is a pretty long FRQ with multiple components, but see if you guys can try as many as you can, or get as far as you can. I'll give you a little bit more time for this one. Let me give you guys about 7 minutes to try this, but see if you guys can get all of this done in 7 minutes, which is a pretty good pace to get it done. A lot of it's pretty easy, like equilibrium constant expression, so on and so forth. But just try to get as much done as you can, and then we'll start it after 7 minutes. Okay, so for A, you got to write the constant expression. This one's pretty simple. We're just going to write K. Oh, why did I put a bracket there? Crazy. K is the concentration of the product, so Al3+, and Cl-, but since the coefficient is 3, you cube it. If you notice, this is a solid, so we omit it, so it's pretty much over 1. So we can omit the over 1 as well. All right, for the next one, we're going to need to use an ice table. But before we do that, let me just talk real quick about what this term saturated means. Saturated means that you have the maximum amount of ions dissolved in the solution. It's another way of saying that the system is at equilibrium. Okay? So saturated just means it's at equilibrium where the solid and the ions have a constant concentration. Okay, so let's do our ice table. So I'm going to write my AlCl3 solid goes into equilibrium with Al3+ and 3Cl-. Now for this one, we don't really have very many numbers, but we can actually get a lot of them just by looking at the system. Okay, so we're going to set up our ice table. So we're going to start with AlCl3. Do we have any values for AlCl3? Nope, it's a solid, so don't need anything. Okay, what are our initial values for the ions? 0, because we're allowing this solid to dissolve. So initially it hasn't dissolved yet, so this is going to be 0 for each of them. Okay. All right, so if we look at the change for the ions, is it going to be a positive or negative change? Positive, because you start at 0, so you are gaining. Basically, what's happening is the solid is starting to dissolve inside of the water. So it's going to be plus X and plus 3X. That will give us our equilibrium concentration of X and 3X. Okay, so we're going to use our equilibrium constant expression now to set up what we have. So the K value is 1 times 10 to the negative 15, and that is equal to Al3+ concentration, which at equilibrium is X, and Cl- cubed, and it's 3X. So 3X cubed. And so if we're just trying to find the concentration, the molarity of Cl-, we just need to solve for X and plug it in for this right here. Okay, so that's how we can do it without any of the actual numbers. We can just use the K value and our ice table to figure out the concentration at equilibrium. So let me give you about a minute or two to do that, just so you can get a little algebra and calculator practice. But see if you can solve for X and find the molarity of Cl-. Just heads up, a lot of people make a crucial algebra mistake right here, so just be on the lookout for that, okay? Double check your algebra. And it has to do with the exponent right here. A lot of people see this and they just put 3x cubed. However, 3x in its entirety is in the parentheses, so you need to cube everything in the parentheses. So on the right side, you'll get x times 3 cubed, which is 27x cubed. Okay. Everybody good? That's the big mistake a lot of people make on this problem, is that they forget to cube everything. All right, so if we simplify that out, on the right side of the equation, we will get 27x to the power of 4. Okay, and that's what we need to simplify in order to figure out x. All right, so we need to find the fourth root of both sides. And if you don't have a function for that on your calculator, it's pretty easy. If whenever you're finding the root of something, whatever you have, you just can put it as the exponent of 1 over that value. So if you have square root, this is the same thing as an exponent of 1/2. If you have a cubed root, this is the same thing as exponent of 1/3. For here, we have the fourth root, so it'll be x to the power of 1/4, which is also 0.25, so you can put it to the power of 0.25. So that's an easy way. If your calculator doesn't have the fourth root, your algebra skills can really help you out right here. So if we're simplifying this, on my calculator, I put in 1 times 10 to the negative 15, and then to the power of 0.25, and that's going to equal, wait, I just tripped out. I'm sorry. I divided by 27 first. My bad. That's easier. So divide by 27. My fault. So you're going to divide by 27 to isolate x. I mean, you could do it the other way, but then you would have to 1/4 the 27 as well. But you're going to do 1 times 10 to the negative 15 divided by 27 first. Sorry about that, guys. Okay, and that will get me, you guys can check my math, 3.7 times 10 to the negative 17. Okay, and then from there, to get rid of the power of 4, that's when you would put it to the power of 0.25 or 1/4. Okay, and so x should be about 7.8 times 10 to the negative 5. Yeah. Yes, you will have to do that. Yeah, so we're not done yet. We still need to find what the question's asking for, which is molarity of Cl. So we plug in x right here, so just it's this times 3. Yeah, great catch. Okay, so you should get 2.34 times 10 to the negative 4. Make sure you label it properly. It'll be molarity. So this right here will be your final answer. Okay. So pretty easy in terms of the ICE table, but then this one, the algebra can really get you, especially if you forget to cube the 3, and also if you don't know how to find the fourth root of a value. Okay. All right, any questions on B? All right, C is kind of a throwback. For this one, we will have to do stoichiometry dimensional analysis. And since it's been a while since we did that, we're going to just go over it together. Okay? All right, but everybody good with this value for B? Okay. I'm going to jot it down up here just because I need some space. Concentration of Cl minus at equilibrium is 2.3 times 10 to the negative 4 molarity. Okay. All right, so what C is asking is what is the maximum amount of AlCl3 that can dissolve in 200 milliliters of water? So what this is basically asking is, if I have 200 mils of water, so I got a container, right, 200 mils of water, and you have AlCl3, how much of this can dissolve inside of this solution? And in order to do that, we're basically just looking at how much AlCl3 do you need to make a saturated solution? So, very easy to do this. We just start with the value 200 milliliters, okay? So we're going to start with 200 milliliters. First thing that you want to do is convert it to liters, because if you look at all the concentration stuff, it's all molarity, right? Molarity is moles over liters. So we're going to convert this to liters. You can divide by 1,000, but I'm going to set up the ratio right here just so you have it. But if you want to start the calculation with 0.2 liters, that's fine as well. If we do that, we get rid of milliliters. All right, after that, we want to figure out how much AlCl3 can dissolve. We're going to figure that out by figuring out how much of your ions you have at equilibrium. So we just got the value for Cl, so we can just plug that in. We know that at equilibrium, there's going to be 2.5 times 10 to the negative 4 moles of Cl minus per liter. Because molarity is moles over liter, so this just turns into moles divided by 1 liter on the bottom. That will allow us to cancel out liters. But it's not asking us for Cl minus, it's asking us for AlCl3. So we got to convert this to AlCl3, and it's very simple. We just need to figure out how many moles of Cl minus are in 1 mole of AlCl3. Okay, so if you look at the formula, how many Cl's are inside AlCl3? 3. So it'll be 3 right here. That'll allow us to cancel this out. And then from here, you just use the molar mass to find the grams of AlCl3. Okay, so kind of a long procedure, but just cancel out the units. It's just standard dimensional analysis. So see if you guys can figure that out. Use the molar mass to find grams of AlCl3. You will need your periodic table for this. Okay, and as you're doing that, if you have questions on any of the steps, please let me know so I can answer them. But if you got it, then see if you can find grams of AlCl3. Okay, so molar mass of AlCl3, I got about 133.3. Everybody good with that? Around there. 3.5. Okay, you just add 3 chlorines and 1 aluminum. And then you solve this out, and you should get something around the lines of 0.002 grams of AlCl3. Okay, if you got 2 times 10 to the negative 1, 2, 3, that's fine as well. Either of those work. Okay, so just keep that in mind. I believe you have a question like this on your exam. You will have dimensional analysis, so if you're a little rusty on that, might want to go back, do some dimensional analysis stuff, just to make sure that you're comfortable. Okay. All right. We'll do D and E, and then we'll go on our break. So for D, it says 7 grams of solid AlCl3 is added to 2 liters of a saturated AlCl3 solution. So just to kind of paint the image of what's going on, you have a solution, and this is saturated. Okay, what means it's at equilibrium already. Okay, everybody good with that? And then what you're doing is, while it's at equilibrium, you are adding 7 grams of AlCl3. So you're adding more of your solid. It's saying, if you assume no volume change, are you going to increase Cl minus, decrease it, or remain the same? So I'll go over this with you because it's kind of a funky little phenomenon that kind of goes against what we were talking about, but it makes sense if you think about it. So normally, we would see this and say that, hey, I am adding reactant, right? So if we add reactant, normally we think about how it shifts it to the right. So a lot of people for this problem say increase, right? That makes sense, right? You're adding reactant, it's going to dissolve more. But because I'm talking about this, you obviously know the answer is not increase. Okay, and so let's talk about why. The system is already at equilibrium, right? So if this is at equilibrium, that means you're already at the ratio, perfect ratio of reactants and products. So that means that even if you add more solid, it's not going to cause it to dissolve more. Okay, so keep that in mind if you want to jot that down. So when you have a saturated solution, okay, adding more solid, okay, it does not mean that you have more dissolving. Okay, and the reason why is because it's already at equilibrium. And if you look at it at the ice table, we omit the solid, right? The solid does not play a role in that ratio of reactants to products. So you can add as much solid as you want, but it's not going to increase the amount that dissolves. So if you think about like just everyday life, if you have a bucket of salt water, right? If you dump a lot of salt in it, does it make it dissolve more? No, eventually it gets to the point where it stops dissolving, right? And it just clumps up at the bottom. That's what's going to happen right here. That's what it means for solids to not play a role in equilibrium. Eventually, all the ions that can dissolve already dissolve, and then you can add more, but it's just kind of going to stay as a solid on the bottom. So the answer here is actually going to be remain the same. Okay, and the reasoning for that, again, is that it's already saturated. If you add more solid, you're just going to get more solid. You're not going to get more dissolving just because you're adding a reactant. And again, that's why solids do not play a role in the K value. Okay? So a little counterintuitive, but if you think about it, it kind of makes sense why.
Well, no, it's not. They just not decide.
Hey, don't blame me. I would... No?
All about just dude, 12, 13, 14.
Dude, if I wanted to do something devious, I would, and I wouldn't smile about it. I'd be cackling.
One day to take the test, and then like you act like the one day is kind of like
Yeah, at least
not really.
I agree with you, Wesley, but nobody in this class is gonna want to
You're
take it.
like very deep in
Yeah, you're right.
If it's like a vote and he's gonna have us raise our hands, it's literally gonna be maybe
when
like 6 people.
you live right next to Ralph's, you can let all the groups in.
I'll still vote. I just don't even know why he's fast because the opposite. He already knows that. Everyone's lazy. People will pick the lazy thing.
It's the illusion. It's the illusion of choice.
Illusion of choice.
I already know how it's gonna play out.
So much for
Yeah, like said, there were some parties. I can't even. I have to Okay, can we take it on like the 27th instead of the 29th? Mr. O. Why?
Yeah. You're literally just gonna watch lecture videos and take notes and do the homework, smart work, and take a test. It's actually less room for error.
Yeah, because you mess up every single.
Yeah, like each class session will be super chill. Like you could do nothing, but
Yeah, I know, but I look.
yeah, it's not gonna be good for you. So, your call.
Mr. O's of Christmas past.
Mr. O, can we use the review on our quiz right now?
Good question. I didn't even think about that yet.
Are you making the quiz right now?
Yeah.
What kind of question did you pick?
Number 37.
What?
37?
That's not the 7.
It'll be 6-7. This generation's so cooked. How many people are in this class?
It's gonna be my cake for the party. I'm calling it a party.
You said, did you buy a cake for the party?
Is it just we're going and
We're just going and sitting there for 10 minutes.
we're going to lay on my bed and
Dude, I think I'm gonna right. Right.
I need backup, bro. Cartha needs backup. No, bro. Cartha needs backup. Oh, I'm not kindergarten.
Just get me my grades. I swear.
How do you get no grapes?
Sam, all you getting sour grapes, bro.
Bro, I'll take sour grapes. Oh, all grapes.
Okay.
I write them all out here. I was pissed off.
Alrighty, guys, let's get ready for the quiz. If you can put everything away.
Yeah. I know it's
No, no notes.
I wish we could use our nose.
Me too.
You know you have the choice to let us.
Can I paint my case?
Huh?
Please?
What case?
Just know it's on.
Equilibrium.
That's pretty easy.
Alright, guys. Longer you take, less time you'll have on test.
Do I need a periodic table?
Yeah, you'll need your periodic table. Lily, can you give her a calculator? Thanks. Sorry, I'm counting right now. My bad.
Why didn't you?
One cow.
I guess.
Remember how nobody remembered how to do the one? And then you're giving us one.
Sucks. Alright, guys. As you're getting ready, a couple things. Let's talk about the actual dates for the exam. Oh, there's only 10 minutes left. I know, we might